All right, let's look at the three types of nuclear decay: alpha decay, beta decay, and gamma decay. These are part of nuclear reactions, which means just a reaction that affects the nucleus of the atom. When we talk about a chemical reaction, we're talking about the electrons, the valence electrons interacting, being shared or transferred. But for a nuclear reaction, we're talking about protons and neutrons either changing or being shot off of the nucleus of the atom. And so we have a vocab term here, transmutation, that refers to how one element can change to another element if you add or subtract protons from that element, then it becomes a new element. We also have this key point here that we're going to see later about nuclear reactions, and it's that the total atomic numbers and the total mass numbers will need to be equal on both sides of the equation. When we talk about nuclear decay, and you're going to see a little bit in this presentation, those numbers have to be equal on both sides of the arrow. That's what we mean by both sides of the equation. Okay, let's introduce these particles, and we're going to see slide after slide of comparing them. So we have this alpha particle, which is really a helium nucleus. If we look on the periodic table, that's element number 2, so 2 protons. And we're going to find that it also has 2 neutrons to have a mass of 4. Our beta minus particle, there is also a beta plus, but we're going to focus on just beta minus, just keep it simple. And that's where a neutron converts into a proton. So thinking about transmutation, you can see how that would change the element. We're going to, if something undergoes beta minus decay, then it increases its atomic number by 1. The particle that's being emitted is actually an electron. So we're not going to get into it too much here, but the thing that's being shot out and emitted as radiation is an electron. But how does that affect the nucleus? We're going to see that a neutron turns into a proton. And then finally, we have this gamma ray, think the Hulk. And this is not really a particle, it's high energy radiation. Okay, and so this is like the electromagnetic spectrum, high energy. It's like visible light, but higher energy and shorter wavelength. Okay, I like this slide because it's a really good visual. And so let's focus just on the pictures here. Our alpha decay, we said that that's a helium nucleus. Well, there it is. You can see it there. If you think of that, these little red spheres as little protons. There's your protons, and then you've got 2 neutrons there. So you can see that this is our helium nucleus. When you see this symbol, that's what we're talking about. And really, there's no electrons, so it would have a +2 charge. So just for fun. Okay, how about our beta decay? Well, we said that that's where a neutron converts into a proton, and this is our high energy electron that's being shot off. Okay, and so when we're thinking about what's the effect on the nucleus, well, if you shoot off 2 protons and 2 neutrons, well, that's going to affect your mass, and it's going to change the element down by 2 protons. If we turn a neutron into a proton, we're going to go up by an atomic number of 1 on our element. And then what about gamma? Well, gamma, that doesn't change the nucleus at all. Okay, and so you can see this nucleus before and after both look the same. It's just that one was in its excited state, and then the daughter nuclide is in its relaxed state. Okay. Yeah, parent nuclide, daughter nuclide, those are just vocab terms for the starting nucleus, like here, and the ending nucleus, like here. Okay, let's look at the symbols for each of these. Our alpha particle is a helium nucleus. You might also see this as like this alpha symbol. Both are the same thing, okay? The beta, you can see is an electron, and you might also see it written this way as well. And then the gamma ray, you can see nothing for mass, nothing for number of protons, and looks like a Y. It's that gamma symbol. Okay, something else that's going to be an important point to compare is what would it take to stop each of these forms of radiation? And so what you see is a nice visual here as to what would it take to stop an alpha particle. Well, an alpha particle can be stopped by something as as flimsy or as simple as a piece of paper or cardboard. Okay, they're bigger, and so they're kind of easier to stop. Now they have a lot of energy, but since they're so big, it is easier to stop them as compared to, say, this beta particle. Well, that it's going to take something like plastic or aluminum to stop a beta particle, a little less ionizing energy, but harder to stop. And then finally, this gamma ray, you would need something like a sheet of lead, which is why when you take an X-ray, you need to put like that lead vest on because, well, just like X-rays, gamma rays are part of the electromagnetic spectrum, and so a lead vest is necessary to stop those forms of radiation. Okay, real quick, we're going to zoom in on each and look at an example of a nuclear reaction. Okay, again, this should be reviewed. 2 protons, 2 neutrons bound together. Excellent, we've already seen that. A positively charged helium nucleus, just another way to describe what an alpha particle is. High energy, low velocity. We just saw that it's stopped by a thickness of paper or skin. And here is our nuclear equation. Okay, and we said that we have to have our, on both sides of the equation, we need to have our atomic numbers add up. Do they? Well, let's look. 2 plus 88, does that equal 90? Yes, it does. Okay. And then what about our mass numbers? Let's change our color here. Does 4 plus 226 equal 230? Yes, it does. Okay, that's good. So on both sides of the arrow, the protons, or the atomic number, which is the protons, on one side have to add up to be the same as on the other side, which is what we see here. And so how might we understand conceptually what's happening here? Well, this thorium is undergoing alpha decay. So we would say it's undergoing alpha decay, which you can see the alpha particle right there, to produce this daughter nuclide, which is radium 226. Okay, so this is the parent nuclide, just to use our vocab, and it's undergoing alpha decay to produce the daughter nuclide of radium 226. Okay, let's look at this beta minus. We still have a nuclear equation here. We said that it's an electron, which is ejected when a neutron turns into a proton. The electron is what's being shot out of the nucleus. It's high velocity, low energy. We said that it's stopped by aluminum or plastic. And here's our nuclear equation. Let's check again to see. Here's our arrow. So we want both the atomic numbers to add up to be the same as the other side of the arrow. Well, -1 plus 92 is 91, so that checks out. What about our mass numbers? 0 plus 234 does equal 234. And so, again, both sides of the equation add up to be 0. Excellent. So what's going on here? Well, our parent nuclide, protactinium, is undergoing beta decay, which means that we said that a neutron turns into a proton. So it makes sense to me that this mass number is unchanged. And we see that it's the same, right? Well, that's because a neutron and a proton have the same mass. So what has changed? It's this number of protons. If a neutron turns into a proton, then it makes sense that we've added a proton